Okay, we're starting our next unit, Unit 6 we're going into, which is torque and rotational motion, but we're going to start with rotational motion, actually. So this is going to be in Chapter 10, just FYI, all these assignments will be out of here. So to start with, we need to talk about a couple concepts before we can get into rotational motion. So what we've learned so far has been translations, which is motion in which all the points of a rigid object move from one point to another. So if I have a bottle here, we've learned that it can move like this. We know it can move kind of in two-dimensional motion as well. It can go up and down. But all of the points move together, and the object really stays oriented the same way. We haven't talked about this, where this point is moving to a different place than this point over here, right? If I'm talking about this point of the bottle coming down versus this point of the bottle coming up, that's not a translation, right? We've only talked about motion where the object stays oriented the same way. Now, what we're going to make sure we differentiate between here is an extended object, which is a system or an object in which the pieces are connected but don't have to move together. We've only looked at situations where, again, all of the points move together. Maybe they don't have to, but we've only looked at situations where they do, right? So as an example, a person. We've looked at a lot of situations where we are dealing with a person's motion, but we've only thought about it as it's like this person, I could pick them up and move them over here. But we know that people, we're connected, obviously, my limbs are connected to me, but I can move my arm and not have to move anything else. So now we're going to be talking about these situations where, yes, all the pieces of an object are connected, but they're going to move differently. Now, an extended object whose pieces cannot change position, what this means is independent of other points. So I am just an extended object because I don't have to move the rest of my body to move my arm, right? But we have something called a rigid body where, again, the pieces are connected but don't have to move together. We're going to talk about that in the next example, but they can't change position independently. So my little Totoro here is called a rigid body. If I flip him, which is going to be a rotation, they all change position together relative to each other, right? Again, I can move just my hand and not move the rest of my body. I can't do that with Totoro. He doesn't have joints, yes. He has to move all together. So he would be called a rigid body. I can turn him, but I would just be called an extended object. I can move my arms and my legs and not have to move everything else. So again, another example of this is a Ferris wheel. The center of the Ferris wheel doesn't move, which is why we would call this an extended object. The center doesn't move while the rest of it does. However, it has to move together versus, again, me being able to move my limbs independent of everything else. So again, what we're going to be talking about in this whole unit is going to be basically rotations, which is motion of an extended object around an axis. So if I have my Totoro here, the axis would be like his belly, and I'm rotating him, right? That's what we're going to be looking at today. This is different motion than just straight line, right? Very different. So some examples of rotational motion here. We have a ballerina. She's doing what's called a pirouette. And she is staying in that one spot, and she is spinning, and she stays in that position. We have a Ferris wheel where we have rotation around this point. We got the Earth where we're tilted on that axis and we rotate around that axis. And we have a bicyclist where the wheels are turning, which cause him to push forward. So when we're looking at these different examples of rotation, some objects can rotate without translation. What this means is like this. If I just took my Totoro and rotated him in place, he didn't move. The example I was showing before was this, right? That's rotation with translation. This is just rotation. It's staying in place. So which of these examples above do that, where we only have rotation, but we don't have any other type of motion. Well, that would be the ballerina and the Ferris wheel. The Ferris wheel and the ballerina stay in place. The ballerina stays on point and just turns right there. So that's just rotation. Whoops. And the Ferris wheel just rotates here. It doesn't go rolling off. That would be terrifying. It's one of my fears about Ferris wheels. Besides the height. So those rotate but don't move. Again, that's what rotation without translation means. So looking at some objects, though, can both rotate and translate at the same time. So obviously, looking at the two that are left, we're talking about the Earth because, yes, we're spinning about the axis, but we're also rotating about the about the sun at the same time. So the Earth is rotating and translating. Now, I know that's weird because technically the Earth is just rotating and rotating, right? It's doing this and then rotating about the sun. But we can talk about that as a rotation and a translation. It's moving as it's rotating. As well as the bicyclist. Bicyclist. The wheels turn, the wheels are rotating, but as they rotate, it pushes the bike forward. So that is rotation with motion. Now, to make some things simple, right now we are going to limit ourselves to rigid bodies. So remember, we said rigid bodies have to move together. So a Ferris wheel is considered a rigid body. Technically, the Earth is a rigid body as well. Obviously, there's lots of surface stuff happening on the Earth. That's motion, right? We can have volcanoes erupting and the plates shifting. But really, as a whole, the Earth is rigid. It can't move independently from its parts. So we are only looking at these bodies again that are going to move all together. We're going to assume the rotation axis stays the same throughout the whole time. We're not going to say that it changes, as well as that the center of mass does not move. We're going to make those assumptions to make things easier for us. So imagine this scenario. You have a wind turbine. If you've ever seen those before going to California, I always am like, oh, the turbines, we're here. Has blades that move because of the wind. So looking at this turbine, the center of mass is basically where, if we're ignoring the pole, is going to be where the rotation is occurring. So where is the center of mass? Well, it's right there at the center of the blades. That's its center of mass. It's all concentrated right there. The rest of the mass is kind of going around it. And is the object rotating? Well, yes, the blades are turning, right? We have rotation around the axis. In this case, is once again that center right there, the center of the blades. So its center of mass happens to be its axis. This is mostly what we're going to be looking at. That's where it rotates around. So I know sometimes when we think axis, we think a straight line, but it can be a point as well that we can call the axis. Now, is this considered a rigid body where the points cannot change position independent of each other? Again, my arm can change position independent of the rest of my body. So I am not a rigid body. Or is this an extended body where the points in the object can change position? That's what that says. So I am an extended body. What is this? Is it a rigid or extended? This is going to be a rigid body because the blades have to turn together. One blade can't go spinning off on its own while the rest just like sit there and don't do anything. So once more, a rigid body means if one point moves, the other has to move as well. Now again, this is a rotation because they're not moving in the same direction. If this were a translation, the points would move the same way. They are moving together, just not in the same direction. Now, we also want to talk about this later. Where is the blade moving the fastest? If you kind of look at the picture, you can tell we have this whole long blade here. If you sat on the blade or if you held onto it, where do you think you'd be going the fastest? At the ends of the blade, actually. If you can see in the picture, it's actually blurriest towards the end of the blade. It's really blurry out here. And then right here, it's actually a bit more solid. That's because it's moving faster at the edge of the blade. We're going to talk about that in a bit here. That's going to be part of this lesson of why that happens. But if you attached yourself to the end of the blade here, you'd be whipping around. If you held on to the blade right here, you wouldn't be feeling like you're moving as fast. So a couple more details here. I meant to put that as a fill in the blank, but that's okay. So angular displacement. Let's work up to talking about angular velocity and just regular speed when we're dealing with rotation. So to start with, we need to talk about angular displacement. So angular displacement is the change in the angle. So that's delta theta. However, we're going to be dealing in radians. Yay. It's going to be a lot easier than you think, though. I know I'm not a huge fan of radians because we don't use them as often, and I always forget them. But it's actually going to be easier than you think. So instead of degrees, it's radians that we're working with in this unit. Now, that is the distance that a point on the rotating object moves in a given time interval. So again, really, we're talking about the angle. So angular displacement is the angle displacement, if you want to think about it that way. So a point closer to the axis is going to move a shorter distance. A point farther from the axis moves a farther distance. We're going to talk about that a bit more later because dealing with angular velocity, we don't care about this yet. So we're going to come back to this. So angular velocity, this is omega. It looks like a W. That's actually omega. You might see it written a little bit differently for like sororities or something, but that is omega. This is the angular displacement over time. Normal velocity is displacement over time. So angular velocity is angular displacement over time. So we call this the average because we're just going to kind of, again, we could do the instantaneous, but most of these questions will be dealing with the average change of angle. So here's my angular displacement. That's my change in the angle over time. Now again, how we measure this, because we're measuring the angles in radians, this is radians per second, or again, rad per second. That's going to be the units for angular velocity. So if we do not have our measures in radians, if we don't have our measures in seconds, we need to make those conversions unless it's a multiple choice question and in it it's talking about minutes or hours or something like that. So keep an eye out for that. Now, for any rotating rigid body, which is what we're focusing on, right, where again, the points all have to change together. They can't change independent of each other. The angular velocity is the same at all points since it's based on the angle change. So when we're talking about angular velocity, it's actually the same for all points. What we said earlier on the wind turbine, whatever that thing's called, it feels faster to you if you latched on to the end of the blade versus right close to the center. It's going to feel faster. But angular velocity is based on the angle change. And it's the same angle change no matter what point you're at. So if you notice, if this was my wind turbine, we can think about it like this. If I'm latched onto this point here versus you being latched onto this point here, when we deal with the angular velocity, let's say we do this rotation. How many degrees is that? We'll just say degrees for right now. How many degrees of a rotation, if I started here and rotated here, how many degrees of a rotation is that? That's a quarter rotation. That's a 90-degree rotation. We're going to talk again more about that in radians on the next slide. So even though they're at different points, they experienced the same angle change, right? They both experience a 90-degree angle change. So when we're talking about angular velocity, it's the same for all points. So we're going to come back to what's different between those points on the next couple slides. Now, when we do these questions, we have to, again, because we're talking about velocity, direction matters. Normally, this is weird, but we call counterclockwise the positive direction, and here's kind of why. Well, it's weird. This is counterclockwise, right? If you're looking at the bottom, it looks like you're going to the right, so that's the positive direction. And then clockwise is the opposite direction. So normally we call this positive and this negative. But you can choose, you just have to be careful, because if we change direction, that is a change in the velocity. So we got to be careful with that. So again, clockwise is negative, but it doesn't matter. As long as you're consistent throughout, you can choose what you want to call the positive or the negative direction. Okay, let's talk about radians now. Now, if you're in calculus or pre-calc or whatever, you might have already been talking about radians. So we're just going to do a quick review here. And like I said, it's going to be easier than you think. Okay, so radians are based on the measure of the circumference of the unit circle. So remember, our unit circle has a radius of 1. So do you recall what the circumference of the unit circle is? The circumference of the unit circle is 2 pi. Circumference formula is 2 pi r. So if we have a radius of 1, that's 2 times pi times 1, that's 2 pi. So radians are based off of this fact, that a full circle, a unit circle, has a circumference of 2 pi. So 1 full rotation per second is the same as 2 pi radians per second. Again, a full rotation is 2 pi around. So this is a conversion we're going to have to work with. Again, they're going to use the term revolution. So 1 radian per second. Ooh, let me fix that. I'm sorry. This should say 1 revolution per second. So 1 revolution per second, excuse me, equals 2 pi radians per second. Once again, a full rotation is 2 pi. So we want to make sure we're converting to radians per second when we're dealing with angular velocity, because that's how it's measured. So as an example here, we're going to have a question about this later, but a turbine blade, which is just on, again, a windmill basically, rotates at 25 revolutions per minute. So that means in a minute, it goes around 25 times. We want to know what this rate is in radians per second. So we're going to do our conversions like normal, where 25 revolutions per minute, where I'm going to multiply by things on top to cancel out what I have on bottom. I'm going to multiply by things on bottom to cancel out what I have on top until I end up with what I want. Our end goal is radians per second. So I'm going to go ahead and start by getting rid of the revolutions. Now, if I want radians on top, I need to multiply with radians on top, because that's what I actually want on top. And therefore, revolutions will go on bottom, because that's what I want to cancel. Go very slow when you're doing this. We haven't done a ton of more difficult conversions like this. So we know, based on this statement up here, that 2 pi radians are in every revolution. So 2 pi radians equals 1 revolution. So that takes care of getting rid of my revs, and now I have radians on top. That's what I want. But I also need to have seconds on bottom. So if I want seconds on bottom, I put seconds on bottom, and then I put on top what I want to cancel. I want to cancel out those minutes. I don't want minutes anymore, right? So we know this. Go ahead and fill this in, though. What would be my numbers in this fraction? Well, 1 minute has 60 seconds. There we go. There's our conversions. We multiply across the top. We got 25 times 2 pi. So that's 50 pi radians over, my minutes are gone, excuse me, over 60. And then we can actually just plug this in the calculator, seconds. And this is going to give us our answer. Your answers are going to be mostly in decimals. So 50 shift pi divided by 60. So 5 over 6 pi, or, oops, delete. Oh, come on, we can delete this. Go back up. Or this comes out to be 2.62 radians per second. So again, usually you're going to have your answers like this in a decimal. Okay, so let's keep going from here then. So we're going to keep that in mind. We're going to practice that in just a bit more. So keep in mind, though, that when we are looking at rigid bodies, speed is different than angular speed, or velocity is different than angular velocity. Because like we said, any points on the object are going to move their distance in the same amount of time. Yes, again, now they move the angle in the same amount of time, which is why the angular velocity is the same throughout. But when we're looking at the actual distance they travel, when I do my 90-degree rotation, they rotate that angle in the same amount of time. So once again, angular velocity is the same. But this little dot right here only had to travel this distance, if we were to measure that with the measuring tape, versus this dot traveled that distance. So when we're looking at actual speed, finally we're here now, actual speed, the distance they travel at different points is different. So I want to show this to you. If you guys have ever been on a ride called the Gravitron, you've probably been on something similar. But it's basically the centrifugal force ride. I'm going to go forward a little bit. There's always an operator in the center, and he just kind of sits there and looks like really pissed off that he's not having fun, that he just sits there while the ride goes on. And then everybody else starts to spin around. There's crazy music and flashing lights. The guy in the center still just looks like he's just sitting there like normal. And eventually, if you've ever been on this ride, what happens is as it goes faster and faster and faster, these little, yep, there it goes. These little, I don't know what you would call them. The walls basically shift upwards because we're going faster and faster. That's based on centrifugal force, which we kind of skipped, but that's okay. So this guy in the center has no distance from the center, right? So he's just sitting there like, this is fine, whatever. He just spins kind of slowly. People on the outside are whipping around faster than he is. He doesn't feel like he's moving that fast. They feel like they're like, wah, and that's why they get stuck up against the wall. Oops. Where am I? There we go. So when we're talking about the actual speed, so very important, guys, if they say angular speed, that is a different thing than speed. Kind of weird. So the speed, so we're saying v, of any point on a rotating body is r times omega. You can probably guess what r is because we're talking about a rotation, so that's circles, right? R is the distance from the axis. Or you can think about it like the radius, yeah? It's the distance from the center, wherever we're rotating at. And omega is what we were just talking about, angular speed. So we do need to know the angular speed in order to find the actual speed. So this is, again, the actual speed that if you latched onto that rotating body and whipped around, that you would feel. The closer you are to the center, the slower you feel like you're going. The further away you are, the faster it feels like you're going. So once more, make sure we have that down. We got these two different formulas. Angular speed was change in theta in radians over time. And this is r times that angular speed. So we're just going to do a couple quick questions. I know this has been kind of a long video, but we're going to come together and kind of work through some harder stuff. But I wanted you guys to see these. I'm just doing it in one huge long video. So talking back to, this is comparing angular speed versus just speed. So we talked about that turbine blade before, but now this turbine blade is rotating at 20 revolutions per minute. What we want to know is how fast in meters per second. Keep in mind, I will say, guys, sorry I didn't say that here, if you want to write it down. This is still meters per second when we're talking about speed. Angular speed, radians per second. Regular speed, meters per second. So is a point on the blade moving that is 0.5 meters from the axis. So how fast in meters per second means we're using V equals R times the angular speed, or again, omega. So we need to know what this is in radians per second. We have it in revolutions per minute. This is the angular speed, but it's not in the right units. So I want you to try it real quick. We just did it before. Try it one more time. Get 20 revolutions per minute into radians per second. Look back to that question we just did if you need to try it. Okay, so to get to radians, I know that there are 2 pi radians in 1 revolution. And there in 1 minute, there is 60 seconds. So this is 40 pi across the top, 60 across the bottom. Cancel, 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 cancel. Good, I got radians over seconds. And I'm just going to plug this in the calculator. So 40, delete. 40 pi divided by 60. Fraction of decimal. So we get 2.09 radians per second. So this is the angular speed. So all we have to do then is plug this in to find the actual speed times the radius, how far we are away from the axis. Go ahead and try it. So we are 0.5 meters away from the axis. We found out that our angular speed was 2.09. So what is this? 1 point something. 2.09 times 0.5. Oops. 2.09. We get 1.045. I'll go ahead and use all of it. Meters per second. So they're actually not moving that fast. Go ahead and try this next one. It's the exact same thing, but now we're moving 1 meters per second. Keep in mind, sorry, we're 1 meter away now. Keep in mind the angular speed is the same, even though we're at a different point, the angular speed is still the same. So what should we do here? Well, if my angular speed is still the same, all that changes is now I'm 1 meter away. Angular speed doesn't change because the angle doesn't change, even if I'm at a different point. So in this case now, we're at 2.09 meters per second. Good. Okay, I think what I'm going to do, actually, because this video got very long, very quick, I feel like it's been 40 minutes possibly, I'm going to actually go through these 2 questions with you guys. We're going to pause here, we'll bring it back and kind of check in and see where we're at.